Pleasure to welcome Michael Jordan from the University of California at Berkeley, who will be talking to us about hierarchical Dirichlet processes.
Okay, thanks. I'm really going to give a talk that's part tutorial and part research, probably a little more tutorial than anything else, because I have a feeling that most of the audience is not in the same area that I'm in. And the topic I have in mind is the field of random measures. So a lot of you know about randomness and measures, and I don't know how many of you work with infinite dimensional objects that are random, in particular random measures. And so part of this will be just what are those objects mathematically, what can you use them for, and particularly in what role they play in statistics, which is my home field. So let me start with a slide that gives you a little flavor of some of the kind of problems that we face in our work and the field faces as a whole. So one of these is kind of a trivial problem, and another one's not so trivial, but it's pretty well known what the answer is. And the third is more of the kind of problem we really face in real life, and what my group tries to do is to bring all kind of three of these levels together. So the first problem is one I actually gave in a randomized algorithms class a few years ago, and it's an undergraduate level problem. So take the integers 1 through n, and consider the ensemble of random permutations. So all permutations have equal probability. And now I ask, what's the probability that integer I and j appear in the same cycle? All right, so I'll let you puzzle about that for a minute. Some of you hopefully will know the answer. My undergrads were able to solve the problem. It takes about 2 or 3 pages of sort of just a little bit of calculations, and an interesting answer comes out. So whether you know the answer or not, you might want to think about it a bit, and I'll give the answer later. And think particularly how it scales with n. Okay, so if you know something about permutations, you know kind of about log n and so on, you might think about scales. So here's a little less undergraduate kind of problem. This is a real problem. It's been solved, but it's not a trivial problem. So consider probability distributions which are exchangeable, i.e. for some permutation pi, the probability of x1 through xn is equal to the probability of the permuted values of the random variables, and that's true for all n. So that's called infinite exchangeability. Suppose that's true. So that sort of seems that things, it doesn't matter what the order is. And the question is, what does that have to do with independent, identically distributed variables, what's often called bag of words models? That's where Google, we should say that kind of word. The whole processing of a document at Google is based on it, treating it as a bag of words. If you scramble the words, it doesn't matter. And so what probability structure is implied by adopting a bag of words model? And the third problem is the following. Let's suppose you have a very good clustering algorithm, spectral clustering or k-means or whatever you like. But let's suppose that I have a problem where I want to do this with multiple groups of data, not just one group. I'll give you an example in bioinformatics later. So you run a clustering algorithm on each of several groups, but I believe in some way these groups are related. And so what I would like to do is to solve the clustering problem jointly across the groups. I want to share clusters among groups. So how would you solve that kind of problem? So that's more of a research kind of problem. It's not a math problem. It's a figure out what to do kind of problem, the kind that we really face in real life. And so part of the talk then is going to be about what do these kind of 3 levels of thinking have to do with each other, what do these specific problems have to do with each other. All right, so let me answer the second problem, me being Di Finetti. So Di Finetti in the 30s proved the following theorem. So exchangeability, as I said, is the invariance to permutation of the joint distribution of infinite sequences of random variables. So if you have infinitely exchangeable sequence, then for any finite subsequence, p of x1 through n, has a representation, so if and only if, as a marginal probability, i.e. an integral, under some random measure. Well, let's call this a parameter. So this is some distribution on a parameter of conditionally IID data, i.e. conditional on that parameter, you have independent choice of x from a distribution indexed by theta. Okay, so you would call this conditionally IID, independent identically distributed. Okay, conditional on theta, and then you put a measure on theta, make it be random, and then you add up over all thetas. All right, so one direction of this theorem is really obvious and trivial, that if you have this kind of representation, then these things are exchangeable, because there's symmetry here. It's just kind of obvious. But the other direction is what Di Finetti really proved, that if you have this symmetry, then there must exist some theta and a distribution on theta, 2 together, such that this thing can be represented in this way. All right, so this is a very important theorem. It's sort of the core of at least Bayesian statistics, because if you believe your data are exchangeable, that said nothing about a particular statistical model. It just said that there's some invariance in the world, and that you can often assert about some real situation. If you assert that invariance, then there must exist this mathematical structure underlying the data. So a Bayesian would call that thing a parameter and call that a prior on the parameter and say, given the parameter, there is a statistical model from which you get the data. Okay, you must have that if you have exchangeability. Okay, so that's the Di-Finetti theorem. Now, this theorem wouldn't be true if theta were just a classical parameter ranging over Euclidean vector spaces of the kind you see in elementary classes. Okay? Theorem wouldn't be true. You need a richer structure to make this theorem be true. In particular, theta really needs to itself be a whole measure. Okay? And think that makes sense. And now I'm going to replace theta with g just to make this a little clearer so your mind doesn't think parameter. So I'm going to draw something, a measure, that itself has a probability distribution. And having gotten that measure, then I'm going to draw data from that measure repeatedly. Okay, that's the level at which the theorem is true. Okay, and so this is a rich object here. This is just any old measure, you get data from that measure. So this is what we call nonparametric. It's just anything. Okay, and this says there must exist a distribution on that measure, so you have a random measure. Right? That's kind of where in mathematics the idea of a random measure really comes from, is the Di-Finetti theorem. Okay, so we'll have to talk a little bit about what we mean by random measures, and have this talk not be 4 hours. I'm going to concentrate on a simple version of a random measure, something called the Dirichlet process. All right, so now let's go to the third problem, and then we'll try to tie all these things back in together later. So an important data analysis problem is how to do clustering, and there are many, many ways to do it. You've probably all seen different parts of this slide. Many different fields have developed many kinds of clustering algorithms and so on and so forth. And let me just kind of let you look at that slide for a second. I won't go through the issues underlying them. What we're going to do today is talk about a method that's a little different, something that maybe you've not seen. It's none of the above. And this method is based on something called the Chinese restaurant process, which is a kind of piece of probability and combinatorics. So let's describe it as a stochastic process. So it's a random process in which n customers sit down in a Chinese restaurant with an infinite number of tables. Okay, so the first customer sits at the first table deterministically. So we're going to describe this in some ordering. N customers are going to come in. The second customer, let's suppose this is the first customer. The second customer arrives and sits at that table with probability 1/2, or in general some parameter alpha, and moves to a new table with probability 1/2. Third customer comes in and joins a table proportional to the number of people already at the table. That's the general rule. So it's one of these kind of rich get richer reinforcement sorts of schemes. And there emerges the biggest table and so on and so forth. And you can prove that after n people have come in, you have roughly log n tables occupied. And moreover, as I'll say on the next slide, you can prove that this process is exchangeable. Actually, I don't have that on this next slide. I will prove that in a minute, that the process is exchangeable, that even though I described it with a particular ordering, the customers came in 1 through n in a certain order, that the partition that you induce on the customers is invariant to ordering, i.e. who's together with who at what table, or who's together with who is invariant to the ordering. So we'll talk about that in a second. Anyway, back to clustering. How would you use this to develop a clustering algorithm? Well, the idea is now we're going to have parameters and data and distributions, so we'll be Bayesian about this. And so when you arrive, the first customer arrives at a table, draws a parameter that's going to be associated with that table from some distribution. So if we're doing Gaussian mixture clustering, for example, so we have these little, round or ellipsoidal things in space. The way that arises is that when the first customer sits at this table, they draw a parameter phi1 from a distribution on parameters, like means and covariances for the Gaussian case. And everybody who sits at that table inherits that parameter. So everybody, that's a cluster, has a certain mean and a certain covariance. And then all the customers are like data points that come from the Gaussian probability with that mean and that covariance. Some other table, whenever someone sits there, they choose a new mean and covariance for that table. So that's some other cluster. Okay? And so as people start to fill the tables, you start to get means and covariances filling the space, and then data points selected from those Gaussian distributions. Okay, so now we have a fully specified probability distribution on everything we could care about. Tables, number of tables, assignment of data to tables, parameters, everything. Okay, so if you're familiar with finite mixture modeling, which is widely used in statistics, it's where you pick the number of tables a priori, k. All right, and then you have a likelihood and you do some statistics with that. Here we don't have that. The number of tables is open-ended. In fact, it grows as a function of the number of data points. That's log n. Okay? But anyway, we have a joint measure on everything in the world, and we can do Bayesian statistics and infer things like the posterior distribution of the number of tables that are occupied, given some data. So I think the next slide has just got a little picture on it showing you doing this with some fake data. There it is. The little blue points are data points. So I've now sampled from an underlying mixture of Gaussians. And then this is the posterior mode, the configuration of everything inside that has the most probability to plot something. I did that. All right, so that's after a certain number of data points, after more data points, and so on. As I get more and more data points, I start to get more and more clusters. That's the posterior mode. Okay, so this is nonparametric. The number of clusters is not being fixed a priori. Okay, so that should be somewhat unfamiliar to you. How can you do that sort of thing? And we'll talk a little more detail about how you can do it. So let me return to exchangeability. So as a prior on the partition of the data, the Chinese restaurant process is exchangeable. Okay? Even though I set it in an ordering, it's actually invariant to ordering. All right? Moreover, the prior on the parameter vectors associated with the tables is also exchangeable. And that sort of follows from the first point. They're closely related. The prior is just, once I have a table, I have a prior. I have a parameter for that table. We can write this out mathematically. Here's the parameters associated with the different tables. So after I've assigned parameter vectors to the first I-1 tables, the parameter for the ith table, for the ith data point, these are the previous I-1 data points. Now the ith data point comes in. It'll either sit at one of the previous tables with this mass, or it will be a draw from a base distribution of parameters that, for the Gaussian case, for example, this could be means and covariances. Okay, so that's just a way of writing the kind of dynamics I described above as a growing probability measure. And this thing is called the Polya-Urn model. And so the description there in terms of the Polya-Urn is just that I have colors in an urn. And I grab one of the balls in the urn, a certain color, and it's either one of the colors that's previously there or it's a brand new color. And the probability measure on colors is G. Okay? And once I've grabbed it, I put it back in the urn with a second ball of that same color. Okay? So that's another way of saying the Chinese restaurant process. That's called the Polya-Urn model. Okay, so anyway, it's exchangeable. And you could just simply take this thing and multiply out all these sequence of conditionals. You'll just get a product of things by the, the chain rule of probability theory, and you'll get the joint probability over I1 through In. Okay? You just take the product of a bunch of these, and you can do that on the back of your envelope. You can do a little combinatorics, and you'll find out that that object is invariant to order. And that's your proof of exchangeability. Okay, so that's an easy little proof to show that this is exchangeable, just a little bit of kind of products and sums kind of calculation. All right, now that you've proved that that thing is exchangeable, you can do all kinds of interesting things. All right, in particular, you can do statistical inference, and we'll talk a little bit about this later. In one of the previous talks, someone mentioned heat bath kind of things and Glauber dynamics. You can do Glauber dynamics with this because of exchangeability, and all sorts of other things. So let's return to the problem I posed earlier in the talk. What's the probability now that integers I and j appear together in the same sequence on the ensemble of random permutations? Okay, so anybody want to shout out an answer, what they think the answer is? One over log n, 1 over n, some constant.
1/2, right?
What do you think is 1/2? Someone else back there said that. Anyone else want to guess? There are roughly log n clusters, or log n the permutations. That's the number of cycles in a permutation, log n. So if it were kind of equal, it should be like 1 over log n. All right. So why is it 1/2? It actually is 1/2.
Because if you have something where they don't appear in the same cycle, you just transpose them, and then you get one that does. So there's a bijection.
Yeah, you can do it. That's sort of. I don't want to repeat his proof. I wouldn't give credit for that in the class. It's kind of. He just transposed things around. That didn't quite work. But anyway, there is a proof that kind of exchangeability is the underlying idea. So instead of just calculating things out, which you can also do, and that takes a couple of pages, a little thought, and this is not much thought, but a little thought shows that cycles in permutations are isomorphic to tables in the Chinese restaurant. And that's in fact why it's a Chinese restaurant, because they have round tables. And people sitting around the table, there's actually that mathematical structure you want to capture. So it's round tables. The Chinese restaurant is exchangeable, as we basically proved just by showing you how to prove it. So the probability I and j appear in the same cycle is the same as the probability that 1 and 2 appear. You just exchange. And the probability that 1 and 2 are at the same table, well, probably the first guy sat at the first table deterministically, and the second guy joined him with probability a half and moved to a new table with probability a half. So the answer is actually a half, and that's the proof. And there's lots of other things you can prove in combinatorics and probability just by referring to the Chinese restaurant. It's quite a little generator of mathematical structure at the interface of combinatorics and probability. Okay, so that was kind of a little bit of background, and so I'm going to now move into some more rich stochastic processes and inference. What can we do with these things? And then the main point of the talk was the hierarchical Dirichlet process, but I don't really want to spend a lot of time with it. It's my research agenda, but I want to give you more of an idea of the flavor of the field. Okay, so I'm going to need a little notation for the talk. And instead of writing out lots of symbols, I like to use graphs to express probability distributions. So hopefully a lot of you have seen graphical models before. This is just a way of writing out multivariate probability distributions. So if I have random variables or vectors 1 through n, in this case 6, I can associate them with vertices of a graph, and then the edges define conditional probability distributions locally. So the joint probability of x1 through 6 is just the probability of, well, x1 has no parents, so it's just a marginal. x2 has the parent x1, so I have a conditional there, and x6 has got parents x2 and x5, so there's that conditional. Chain together the conditionals, and let's use that to define the joint probability associated with the graph. And each one of those little probabilities can be indexed by some parameter, and so this is a parameterized family of distributions. So the undirected case, of course, is the Ising models or Markov random fields or whatever. A little bit of shorthand that we'll find very useful is that instead of drawing this kind of graph, which happens all the time because of the Di Finetti theorem, the shorthand is that you put a box around something, that means you replicate whatever's inside n times and expand out the graph like that. It's just a little bit of shorthand. And then Glauber dynamics or Gibbs sampling is one way to compute on these graphical models. You take one of the nodes at a time, and you form you take all the conditional probabilities associated with that node, its parents and its children. Okay, a little local set of probabilities in the graph. Multiply them out, sample from that resulting object, and that is the new state of that node. And then do that repeatedly at all the nodes in the graph, and that's the Glauber dynamics for a directed graphical model. Okay, and that converges under the usual assumptions to a stationary distribution, which is the joint probability distribution associated with the graph. Okay, so when I say inference later in the talk, that's the kind of thing I mean. That's a simple version of it. There's lots more complicated ones, but that's one way to do it. All right, you also all need to know what the Dirichlet distribution is. I hope that you do. I don't know what this audience is, but a Dirichlet distribution is it's an exponential family distribution on the simplex. So it's kind of like the Gaussian of the simplex, if you will. It's the kind of little bump sort of object. It's got parameters. So the probability of pi now is a set of non-negative numbers that add to 1. So numbers on the simplex. All right, we can put a distribution on them with parameters alpha by taking each one of those things and raising it to the alpha power. The -1 is just a convention to make it look more elegant. And this is just a normalizer. And so this kind of has a bump shape. That's a Dirichlet distribution. A special case of that where the simplex is just the interval from 0 to 1 is the beta distribution. So I've just got 2 of the pi values now. And depending on your particular choice of parameters, there's a bump with alpha bigger than 1. But when alpha is smaller than 1, you get things that go like this. They go the other direction. And we'll be particularly interested in that case. So when alpha is equal to 1, you get the uniform distribution. And then as alpha grows, this thing tilts. And you can go either with positive values of bigger than 1 or smaller than 1. You have all of these distributions. So this is as alpha is increasing, you start to go up and up like this, putting more and more mass towards the left. Dirichlet distributions aggregate. If I take pi I and pi I plus 1, I take those two values and I add them. I still get a Dirichlet distribution. So it has a consistency property under aggregation. And it has a conjugacy property, which is that if I take a random variable z, a multinomial random variable that has k possible values, states it can be in, and the probability of those states is given by pi k, where pi k is a Dirichlet variable, then I can talk about the posterior distribution of pi given I've observed one of those k states. Okay? And all it ends up doing is that you add 1 to the alpha value for the guy that you observed, and everybody else stays the same. Okay. Okay, so Dirichlet and multinomial go together very nicely. You just kind of add counts, and you get Dirichlet distribution alpha values kind of piling up, and that bump moves around as alpha changes. Right. Okay, so just that was a little bit of elementary background, and so let's now move on to sort of building up some more structure. Okay, so another topic I hope you've seen somewhere before is what's called a finite mixture model. It's a Bayesian approach or generative approach to clustering. So the probability of, so if there are k clusters in the world, I know that a priori, then the probability of some data point, x, given some parameters, is that I have one of k possibilities. I choose with probability pi sub k, one of the k possibilities. Having chosen that, I have some parameter, and I get my data from the distribution indexed by that parameter. And I sum over all the possibilities. That's called a finite mixture distribution. Okay, so it's this thing. If these were all Gaussians, this would be a mixture of Gaussians, or they could be whatever other distribution. All right, so there's just an example under the Gaussian case. All right, now it's going to be useful to make this more general to introduce an explicit variable z, which indexes which of the components was chosen for any particular data point x. Okay, so I can kind of expand this thing out as the probability of that indicator variable being equal to 1, and then having chosen that one, then I condition on that, and I get my data from that particular component. Okay, so if I sum over k, it just collapses. I rewrite back to this, and I get this exact same marginal distribution. Okay, so it's just another way of kind of seeing what's, just making more explicit what's happening in a mixture model. All right, now here's the transition that you need to be able to make, which is that finite mixture model can also be written in a slightly different, seemingly more complicated way, but one that we can generalize, which is now we're going to define a measure g, which is just a sum of atoms. So delta is the Dirac delta at locations phi sub k with weights pi sub k, where the pi sub k is summed to 1. Okay? So that's just a little picket fence of heights given by pi k. And it's a finite number of pickets in my picket fence. Okay, and that's a measure. Okay, and so now I could define the process of obtaining a sample from a finite mixture model as follows. First of all, choose from my picket fence one of the particular pickets. Okay, this is just a measure. It's a picket fence. I can choose from that measure. I just get one of the particular pickets. Having chosen that one, now take data from the distribution indexed by that particular picket. And as I do this over and over, I'll get different one of the things chosen, and I'll get my data from them. It's just a way of indexing a bunch of distributions. Okay, and the pi values are the probability of choosing each one of those pickets. All right, so that's another way of saying what we mean by a finite mixture model. And here's now this graphical representation of a finite mixture model, which is that I have this underlying little picket fence G. I pick repeatedly from that G a particular one of the pickets, and then that's an index into a distribution. In particular, maybe that's a location parameter, so it's a mean. And I get data from a distribution with that as its mean. And that's how my data arise. Okay, just it's a drawing to suggest what's happening. Okay? Now, if we want to be Bayesian about this, we have to put priors on everything in sight, in particular on the parameters pi and theta, the probability of picking the pickets as well as the parameters you get associated with each one of these. Okay? And in particular, the first thing you might want to do to be Bayesian about this is to use the Dirichlet distribution for these proportions pi. You would take some concentration parameter and divide by k, kind of make these equal parameters, and that's how you get pi. All right? Okay, and so now we would write out as a Bayesian this fuller model. The last 3 lines are the model we had before, and now we put some distribution on the phi values. Let's call it G naught. You guys don't care too much what it is. It's just some prior that a Bayesian would put on parameters for some model. And then pi is the one you maybe care more about. It's the Dirichlet, it's called the symmetric Dirichlet distribution. Okay, so now we have a fully specified probability model that has everything in sight being random. In particular, now G is now random. It's now your first random measure. Okay, because the pi values themselves that define G here are gotten randomly from the Dirichlet distribution. Every time I sample, I get a new set of heights of my picket fence, and the locations, phi, are coming from some distribution too. Think of the Gaussian maybe as a generator of the atoms. So every time I sample a bunch of phi values and then the pi's, I get a new picket fence. It's now a random measure. And then I sample the mixture model. The rest of the story is the same as before. So that's a Bayesian version of a mixture model, of a finite mixture model, written as a random measure. Okay, and since I'm not spending a lot of time on the statistics here, let's just wave our hands and say we can do Bayesian inference with MCMC or the Gibbs sample or the Galabra dynamics, whatever you want. Just take that kind of graph, take one node at a time, and sample from conditional probabilities associated with it, and it will converge, and so on and so forth. All right, so now let's go on to the harder problem, which is how do we pick K? How do we know? We don't know the number of clusters a priori. How do we handle that? And so now we're going to try to return to this idea of the Chinese restaurant now from a more sophisticated perspective. All right, so the first thing you would think of trying to do, and you run into trouble, it's hard to do this mathematically, is you would say, well, what I really want to do is I want to take G not to be a finite sum, K equals 1 to K, capital K. I want to give myself an infinite number of atoms. I want an infinite random measure. There I wouldn't have to pick K. I would just have all of them having different heights, and maybe they'd tail off in some way, and I would get around the whole problem of having to pick K. Okay, well, okay, let's go back to our probability specification. We have a Dirichlet distribution. It's very symmetric, and we might try thinking of taking K to infinity. Okay? But these things have to sum to 1, and you're going to run into trouble there. You're not going to be able to find such a distribution. The symmetric Dirichlet distribution, as K goes to infinity, does not approach a distribution. Okay, you're going to run into trouble doing that. All right, so there's another way of doing this, which is better. Easier to understand and leads to a mathematically sensible object that we can then generalize. So the way to do this is to do something called a stick-breaking construction. And the stick-breaking construction is straightforward. You take a stick that goes from 0 to 1. That's 0 over here, and here's 1 over here. And you first of all break off a piece of the stick. You break that off, and that amount is beta sub 1, and that's sampled from a beta distribution with parameter 1 comma alpha naught. That's the same alpha naught as before. It's the concentration parameter. Okay, you remember the beta distribution was a distribution on the interval from 0 to 1, and it kind of peaked up to the left depending on the value of alpha. That's the distribution we're going to use. So we'll break off a certain amount and call that beta 1, and then set pi 1 equal to beta 1. All right, and now we'll take the rest of the stick, 1 minus beta, and break off another amount, beta 2, again sampled independently from the beta distribution. So that's some other random amount. Okay? And that part right here is pi 2. So it's beta 2 times 1 minus beta 1. That's this amount. And so on. So the pi values are these things between the intervals here. And they're gotten by breaking off independent beta distributions from beta variables from this stick. All right? So it's clear that these pi values, if you sum them from K equal 1 to infinity, it's going to sum to 1. Because there's only one, it's only a stick that goes from 0 to 1. Okay? So that's the way to get a random distribution on the integers from 1 to infinity. Okay, that's the way to get it. Okay, and so here's in fact the proof that this sums to 1. 1 minus the sum from 1 to k is equal to that, and you could do a little bit of work there and easily show that this thing converges. All right, so now if we use that to define our random measure going up from k to equal to 1 to infinity, this has a clean definition as a random measure. Okay, because these weights sum to 1. So we have now an conceptually infinite picket fence of the decays in some way. And so in our graphical model representation, we can conceptually think of generating a random measure by getting a bunch of picket locations, a bunch of atoms from phi, from G naught, those are the phis, and then the heights of them are given from this stick breaking process. We put them together, and we get this infinite picket fence. Now, having gotten that, we do the same stuff as before. We repeatedly pick one of the pickets, and according to its height, and then having picked it, we use a distribution with that as its location parameter, and we get data. Okay? All right, so if you understand what I've said, you've understood quite a bit. This is nonparametric Bayesian statistics, something you will not see in the undergraduate curriculum or even in most graduate curricula, including at Stanford and Berkeley, but it's sort of too bad, you should. Lots more combinatorics and probability come out of thinking about these objects, and Jim Pittman, I should mention Jim's name, is one of the probabilists in the Bay Area who work a lot on this, and I think he's probably talked in this particular seminar at some point. In particular, you can show under an appropriate definition of convergence that Dirichlet of that converges in the following sense. It's called sized bias sampling, which is that if you take the if you throw darts uniformly at random at 0, 1 sequentially, and you take the stick breaking intervals that we had defined before, and whenever you hit a new subinterval, you set pi I equal to the corresponding weight and increment I. So I'm reordering in a random way whatever intervals I had before, right? And that's called a sized bias sampling of intervals, right? And you can go back and forth between these objects, the stick breaking representation and something called the Poisson-Dirichlet distribution, by sized bias sampling. So I'm doing a bad job of explaining that because I don't really want to spend time with it, but I just want to give you a flavor that there's a lot of interesting combinatorics behind these definitions. Okay, so that's a little bit of probability and combinatorics. As statisticians, we want to use these things now to, given some data, to infer things. And so if those were the definitions of the prior, how do we actually now observe data and go back and infer all the parameters? That's what a statistician goes backwards, given a model, infer things from the data. Right? And so in particular, if I sample a point theta from some infinite random measure, how do I get a new probability distribution from the prior conditional on theta and making it I into a posterior? Or suppose I do this for a whole lot of datas. How do I get a posterior distribution conditional on all of the data so far? Okay, and so to do this, you need to actually get into a little bit more serious combinatorics, or sorry, stochastic processes. And so I need one more actor in my little drama here, which is what's called the Dirichlet process. So you haven't seen that yet. You've seen a whole bunch of other things, but you haven't seen the actual Dirichlet process. I hope that most of you have seen a Gaussian process. Probably you have. So we want to put a distribution on a whole function space. We want to talk about what a random function might be. And one example of that is the Gaussian process. Let's just think about functions on the real line. And so we want to make it random functions on the real line. One way to do that is to specify Gaussian distributions for finite locations along the real line. So pick k locations, make the values at those locations be random according to a Gaussian distribution, and have a multivariate Gaussian on them. Okay? And then do that for all arbitrary collections of locations. And then insist that they be consistent with each other. So if I have k locations and I add one more, I get k plus 1, if I marginalize out the Gaussian distribution on k plus 1 dimensions down to k, I get the same answer as I had before. All these specifications are consistent with each other. Right? So Kolmogorov said if you could do that consistently for all finite subcollections, you have defined a probability measure on the infinite objects, i.e. on functions in this particular case, and that's called a Gaussian process. So you can do that for all kinds of other distributions, not just Gaussian distributions. You can do it for anything else where you can get consistency amongst different sizes of objects. So in the discrete world, you talk about things like Gibbs measures and so on, but in the continuous world, you have all these other distributions to play with, in particular Gaussians and Dirichlet. So remember I talked about earlier, if I take a Dirichlet on a partition of size k, and I collapse two of the cells to get a partition of size k minus 1, the Dirichlet behaves like it should. It adds the probabilities among those cells. I get consistency. So you can now define a Dirichlet process on partitions. All right, so here's the mathematical definition. Hopefully I've now motivated it well enough that you can actually understand it relatively quickly. I have some underlying measure space, let's call that omega, that I'm putting measures on. I have some base measure, which I'm calling G0. Think of kind of a Gaussian or something like that. And now take a partition of that space, A1 through AR. Okay, and now the Gaussian, say, or whatever, G0, assigns a measure to each one of those cells in my partition. Multiply each one of those things by a number alpha naught, a concentration, and I get a set of numbers. That's what these are. Use those as the alpha parameters to a Dirichlet distribution. All right, and then sample from the Dirichlet. And so after I've done that, I've got now R new numbers, which are kind of fuzzed up versions of those old ones. Remember, it's kind of a little bump. The alpha define kind of the center of the bump. I'm getting numbers kind of around that on the simplex. So these things live on the simplex, and they are sampled from a Dirichlet distribution gotten from an underlying partition. All right, now do that for another partition and ask that the probabilities you're getting out of this be consistent among all choices of partitions. And because of the Dirichlet property, you can do that. All right, and now Kolmogorov tells you that you have a consistent set of probabilities. You must have a measure on, in this case, measures. Okay, so that is the definition of a random measure in the full mathematical sense of the term. It's a measure on measures gotten by showing that you can get consistent assignments of measures to partitions. Okay, random measures. Okay, having defined a Dirichlet process in that way, it's actually very easy now to see what the posterior Dirichlet process would be. I.e., I take a random measure and then get a point out of that and say, now conditional on having seen that point, what's the posterior measure? What's the new measure you get having seen that one point? And the way to think about it is that you take, say I've observed theta 1 from a random measure. I take a little tiny cell around that theta 1. And remember how I update Dirichlet distributions? I add 1 to the alpha for the thing I observed, and everybody else stays the same. Okay? And for that cell, I'm adding 1. And that's true for any cell that contains theta 1. I add 1. So I'm really adding a mass of size 1. Even the very small cell gets a new mass of size plus 1 to it. So a new little spike is going up at that location. That's what's happening. All right, so after I've observed a data point at theta 1, in my posterior, I have a spike at that location, and then I have the Dirichlet process everywhere else. And as I add more and more data, I get spikes arising up throughout the space. Okay, so the Dirichlet process is actually discrete with probability 1, and you may now have understood why that's the case. So let me check my time. I don't want to. So we've now defined 3 kinds of objects: a stick-breaking measure, a Chinese restaurant process, and a Dirichlet process. Right? And you may have liked one of them and not liked the other 2. And the nice fact is these are all kind of the same idea. Okay? So the stick-breaking thing is this random bunch of picket fence. If you take a partition of the space on which that picket fence lies and you ask how many pickets are falling in any given cell, it's Dirichlet distributed. So that is a Dirichlet process. Okay? And moreover, after having gotten a data point sample from those pickets, and you ask what's the new distribution on picket fences, all right, that is also the Dirichlet posterior update, and it's the Chinese restaurant process. I have a certain probability of choosing one of the previous pickets, and if I get that, then I add more string to that picket. I add 1 to that. Otherwise, I get a new picket. Okay, so these actually ideas are all closely related. So let me draw a picture that shows you what's happening here at this point. So a Dirichlet process mixture model can be thought in 3 different ways. And this is my favorite way of thinking about it, which is that there's underlying measure on parameters, G0. There's a concentration parameter that sort of says, has a Bayesian, how much do you believe in that underlying measure? And then G is a random measure. You get it by repeatedly sampling from G0 with this stick-breaking kind of process. And then you get one of those guys, you get a data point, and you get a data from that cluster. Okay, so that's often called an infinite mixture model, or a nonparametric mixture model, or a Dirichlet process mixture model. Okay, so I'm going to skip through a few slides at this point. So this is part of a longer talk, which you can find on my website. That was a tutorial on this material. And so there's some material that I kind of left in because I thought you'd want to see it as it blazed by, but I don't want to really explain in detail here. So what I really want to do next is to explain 2 things. One is a little bit about how you do inference with these things, and then how you can use it for various kinds of interesting applications. So the first one is, how do you do inference? And we've already kind of waved my hands at explaining this. You can do MCMC with this kind of model. So this is now an infinite object. We have these infinite random measures. But because of exchangeability, you can actually still do inference. And the basic scheme is the following. Imagine you have the Chinese restaurant process situation, and I'm trying to decide for a given data point which table it should be sitting at, which allocation, which cluster does it belong to at the current point in time. So to do the Gibbs sample or the Glauber dynamics, what you do is you take that data point, you pull it out of the system, and you look at the configuration of all the other variables, and you say, where should I now reassign? What table should that data point go to? Okay, what's the conditional probability of that data point given the configuration of all the other data points? And that's a hard thing to try to calculate until you realize you have exchangeability. And by exchangeability, I can take that data point at the ith table and move it to the end of all the data points. I can move it to the nth slot. And at the nth slot, all the other data points have already arrived and sat at all the tables, and I'm just asking what's the last data point do? Well, it joins a table proportional to the number of people already at the table. I know that. That's the conditional. I don't have to calculate it. It's not hard. Okay, and so then I can now figure out what table it should sit at according to that rule and according to the likelihood. All right, so that took about 20 years for the statistical field to realize. It's not that hard, but it took a long time. Dirichlet processes were defined in the early 70s, and it wasn't until the 90s that people actually realized that you could do Glauber dynamics on them and do inference on these infinite objects. All right, and when they did, then this sort of exploded as a field. It became the keystone of nonparametric Bayesian statistics. Okay, so it's a very simple idea, but it took a long time. One of the main topics I work on in real life is variational inference. It's an alternative method to MCMC. It's not random. It's not flipping coins. It's based on a deterministic optimization framework, kind of a relaxation of an intractable problem into a tractable one, things that should be familiar for other reasons. And you can do that here as well based on the stick breaking representation. So I'm going to actually not show you how to do that. I'm going to skip again over a few slides that if I were giving a longer talk, I would go into some detail. So this is just how you do the Glauber dynamics, and I'm going to skip over that. And I should also add there are a bunch of alternatives. This is a whole little discipline of its own, trying to figure out how to do fast mixing MCMC algorithms for Dirichlet process mixtures. And then the way that you get the deterministic algorithms is that you truncate Dirichlet processes, and you can base optimization algorithms on that. So I'm skipping some slides on that. I did actually write out at the end of the day the equations that you actually need to run on the computer to do inference under a Dirichlet process mixture. It's really just a very simple little 5 lines of MATLAB to do this with a variational algorithm. And I think the next slide actually shows fitting data using variational inference to a Gaussian process mixture. Okay. All right, so let me give an example that'll sort of bring a little bit more home to you why we do this why do we care about these sort of things. So I could easily give document kind of examples, and since I'm at Google today, I thought I might do that, but I decided not to. Here's another example that I quite like, which is haplotype modeling. And some of you may have heard about that from kind of theoretical computer science point of view. I think of this as a good statistical problem. It's just a mixture model problem. So the problem is the following. If we have some genomic region and we have M binary markers, these are called SNPs, or single nucleotide polymorphisms, M locations in which you and I differ, or all of us differ, and a particular pattern of markers along a chromosome is called a haplotype. And I'd like to figure out what haplotypes are there in the world, in the population as a whole. Because that'll tell me something about the founders of the human population and then our various relationships among each other. And the problem is that when you assay in real life in biology, a haplotype, so here's a haplotype, a capital A, there are 2 possibilities. You can either a capital A or a little a. So I have a capital A here, a capital B here, and a little c here. So that's one haplotype. Here's the second chromosome, right? Chromosomes come in pairs. Here's the second chromosome. On that chromosome, I have the other allele, not the capital A, but the little a. And here I have the other allele, and here similarly. So I have 2 haplotypes here for a particular individual. Each one of us, for each pair of chromosomes, have these haplotypes. I'd like to figure out for that individual, what are their haplotypes? If I could look at that diagram, I'd be done. But the problem is that when you actually do the biological assay, you lose the ordering. So you find out that that person has a capital A and a little a, unordered, and a capital B and a little b, unordered, and similarly. But you lost who goes with what? Okay? So to go from data like this, which is what the assay gives you, to go backwards to this diagram, that's called haplotype phasing, and that's one of the major problems in modern computational statistical biology, or genetics, is to go in that direction. All right, now if I only had one such person, and this is a very ill-posed problem, I couldn't do it. Right? But if I have many such people, and I start to see some patterns here of ways to stitch this together that are consistent with each other, I might be able to infer the underlying haplotypes. And that's what people try to do. Can I ask about time? Now my watch just goes about 15 minutes, thank you. Okay, so this is really a clustering problem. And so let me try to convince you that it is by just writing it out as a mixture model. So here is the actual probability of a genotype. Here's a genotype is this unordered set of alleles over here. So as probable, let's try to write a model for that. The probability of a genotype is the following. When I made a new human being, I first of all got a haplotype from their father. I got a haplotype from their mother, all right? Just by reaching into the bag of haplotypes that are sitting in the population randomly. I chose a random father and a random mother, all right? And then conditioned on that pair of haplotypes, I got a genotype, and this probability is just the probability of the assay. All right? Given I know the haplotypes, what's the probability of, if given I had that, what's the probability of getting that? It's just the unordering process. Okay? All right. Now, I don't get to see what the haplotypes are, so I have to sum over all possible choices of haplotypes to get the probability of a genotype. Okay? All right, so that literally is the model. I mean, that is the biology. It's not just the model, it's the biology. Okay, so however, what method you want to use in this problem, you really are solving a mixture modeling problem. This is just a mixture model. Okay? Now, I really could have written this as probably H1 comma H2 and kind of grouped them together, and separating them out from in that way is called Hardy-Weinberg equilibrium, and it's assumed here, and it's assumed in lots of genetics. It's a fine assumption at the first order here. Okay, so anyway, it's a mixture model problem, but the real part of the problem isn't the usual one of finding the probability model for the components, the pi's and the phi's. It's really, how big is the bag of haplotypes? What's K? If you could solve that, you'd know a lot about human populations and genetics. How many haplotypes are there among us in the room? How many are there in the world? You know, was it 10,000 years ago that there was a crisis in the population? It dropped down to 50 people in Africa, and all of our haplotypes, or those 50 haplotypes, are a little bit scrambled up? You know, or what happened? And what's our disease propensities because of knowing, because of that? So it's a real important problem, and it really is the problem of just deciding what's the cardinality of age. Okay, so I got involved in this problem by just me and a student hearing about this problem and realizing this is exactly the kind of problem that a Dirichlet process really nails. This is exactly what Dirichlet processes are aimed for. It's a mixture model where I don't know the number of components. That's random. And I have a lot of probability structure from Mendel's laws and so on sitting there able to help me. So anyway, we did that. We implemented this. We took some data and we did Dirichlet process mixtures, and we compared it to the state-of-the-art methodology, which is something called the phase program by Matthew Stevens. It's a Gibbs sampler kind of thing on a different probability model. And these are different kind of error measures in different regions of the human chromosome. And let's focus on this error measure, which is the one that people tend to care about the most, and let me not worry about explaining the other two. And you want to have small numbers here, and so here's our method, and here's the state-of-the-art, and we're a little worse on one region of the chromosome, and we're better on all the other three. So this is a hard thing to beat. This is a really good piece of work, and many people have written haplotype systems that don't perform as well as phase. So with just doing nothing other than implementing the Dirichlet process, we have a state-of-the-art haplotype phasing system. Okay, so now the last part of the talk is kind of going to move a little bit out of just tutorial mode and try to say what more can you do with this, and it's also some of the theoretical problems that arise out of this area. And this is the last problem I had on my very first slide, which is now we have, I hope you have a more sophisticated idea of what clustering is about than you may have had before. You now talk about clustering where I have infinite numbers of components or unknown number of components and so on. So now we have that all done. Let's now try to solve a more interesting problem. Now we have in the room, in fact, multiple ethnic groups. All right? And we all share certain haplotypes in common. The bag of haplotypes we have are, in many relations, we all originally came out of Africa, probably. So, my haplotypes and yours have a lot in common, but we have a little bit of differences as well. Okay, so if you just take data from one ethnic group and you do this kind of clustering, you'll get certain clusters. And you do it for a different ethnic group, you'll get certain clusters too, but there should be some similarities, and we'd like to find out what those are. Okay? And so you really want to solve multiple linked clustering problems. Okay? And that's non-trivial. In particular, I don't know of any algorithm really that does that, or anybody who's even worked on that. But it's really important. And so that's one example, but you can think of lots of other examples. In particular at Google, you try to do this sort of thing all the time. I want to take a bunch of documents in some area, and I want to find what are the clusters in those documents. What are the words, the topics they're usually called. Then I want to do that on another set of documents, or maybe a set of images. All right? But I believe there's some relationships among these clusters. If I have a bunch of documents talking about the sky is blue and so on and stuff, and I have a bunch of images with blue skies, I want to find the relationship. So clustering problems often want to be solved conjointly with other clustering problems. All right? And I never in these cases know how many clusters there are in each of these domains. Okay, so really that's the problem we want to try to solve. Okay, so last few minutes then is what is a hierarchical Dirichlet process, kind of mathematically, and then how to use it to solve problems. And so let me just say a little bit about why does one want to be a Bayesian anyway? You often probably, if you're not statisticians, you've heard that there's all these debates going on and so forth. And there's priors, are priors good or bad and so on. And my point of view on it is that priors are usually kind of bad. They're hard to set priors. You usually don't know what they should be. You try to push them under the rug. But there's another very good reason for being a Bayesian, which is you can be hierarchical. You can build hierarchical models. You can group things together. And so let me show you a picture that'll kind of help bring that home maybe. Let's suppose I'm trying to figure out how tall people are in various cities around the country. So I have New York, San Francisco, Los Angeles. All right, and theta is the underlying height of people in that city. And then I get a bunch of data, which is the actual observed heights of a few people. All right, and having gotten some data, I could do maximum likelihood estimation to go backwards and assign the mean height for a given city. Okay, so I could get maximum likelihood estimates, here they are, for each of the cities. All right, but suppose that I just happen to only have 5 people in New York, and I have thousands of people in San Francisco and thousands of people in Los Angeles. All right, well, that estimate based on 5 people in New York is probably very noisy, very not trustworthy. I'd really like to use some of the data over here to kind of leak over to there and help me out. Now, that'll bias me a little bit because maybe people in San Francisco are a little bit taller than people in New York because the weather's better. All right? So I might get a little biased, but with all that extra data, somehow I should get a better estimate because of variance being smaller. Anyway, this is the kind of argument that's called shrinkage in statistics. You want to share statistical strength to make estimates be better, and you don't want to do maximum likelihood. So for a Bayesian, this is very natural. All you do is you put a mean height of all people in the world up there at the top as some unknown parameter. And then the heights of people in various cities are gotten randomly from the mean height of everybody in the world. There is a linkage among us. You put it in explicitly. And now I have a graphical model in which I observe data here, and probability things propagate up and down that tree and come down to here and help me with these estimates. All the data collaborate to help me with my estimates. All right, so that's classical hierarchical Bayesian parametric statistics, and it's the main reason, in my view, for being Bayesian. Okay, it solves a lot of statistical problems naturally. Okay, so now that we have hierarchical modeling in hand, let's go back to multiple clustering problems. How would you do that if you have a bunch of clustering problems where you have these probabilities of being in certain classes, the class indicators, and you have a whole bunch of those things? So what do you share? All right, and you don't know the number of clusters in each of these cases, so how do you match these things up? How do you handle this? All right, so the first thing you would try then is that you would have a Dirichlet process. That's what this lower part of the diagram represents. And then you have the outer plate be, I have multiple Dirichlet processes now, one for each group. That's what we're using our new tool. And the way we're going to link them is we're going to have an underlying base measure, which is the same for all these groups. Okay, they're all coming from the same underlying base measure. Right? And that fails completely. And this is kind of one of the main messages of the talk, that something that works for parametric, good old-fashioned statistics completely fails in the non-parametric situation. And the reason is the following, that if I have some base measure that everybody is sharing, so say you're running the program and you're running my new program, you sample from that base measure, you get a picket fence, and then you analyze your data with that. He samples from that same base measure and gets a different picket fence. With probability 1, none of those pickets overlap each other, because these are continuous underlying measures. So there's no sharing. Your clusters and your clusters have nothing to do with each other. We get no shrinkage. All right? All right, so you're a bunch of smart people, so how would you solve that problem?
Wait till the end of the talk. We're also lazy.
Well, you got to use Chinese restaurants. You got to start thinking about dinner already. You got to think about how do Chinese restaurants help me with this? All right, so what you really kind of like to do is to have the base measure not be continuous. If I didn't have continuous atoms to worry about in the beginning, if it was just a discrete underlying base measure, then you get some of those atoms and you get some and they would have something in common. But if I already built in the thing being discrete, if I knew where the atoms were a priori, what am I doing? I already know the answer. All right, and so you'll face that problem again and again in statistics. If you could make it simpler in this way, it would be great, but that would build in too much. And so the answer is do that, but now make it be random. Make it be a random discrete underlying measure. All right? All right, so if you understood that, you understand what our idea was. And we call it hierarchical Dirichlet processes. And all you do is you go recursive. You be like computer scientists. All right, you say that the base measure for a Dirichlet distribution, this G0, which I've been using as fixed before, is now itself a draw from underlying Dirichlet process. So this thing is now itself discrete, because it comes from this kind of object, and it's random. So I don't have to know where it is a priori. And then I pass that in as the base measure to an underlying set of Dirichlet processes, and then everybody shares everything now. Okay, so the picture, I think, will give you the idea. I now have my hierarchy taken to another level, which is what Bayesian methods do. They say there's some underlying base measure, which is the universal generator of all atoms. And then I repeatedly get a picket fence from that. I repeatedly get atoms from that, and that's the base measure which is shared among all the children. All right, and so all these atoms get shared by everybody in sight. Okay, so the rest of the talk, there's a bunch of slides, but I don't want to, I'm out of time basically, and I don't want to get into them anyway, because it's late in the day, but I hope you get a little flavor of what you would do at this point. You would set up Chinese restaurant process, you'd set up sampling algorithms, you'd set up all the machinery, and you just work with this kind of probability model, and you would solve all kinds of interesting problems. So you could do a stick breaking, you could do the Chinese restaurant process, and it now becomes a franchise. What it is, you have multiple Chinese restaurants, and you have dishes in the restaurants that get shared among the restaurants according to the popularity of the dishes, not just the tables in the restaurants. And you get things building up into a hierarchy. And you work out all the probability theory, and you do various applications. So I think I'm also going to skip through all the applications, just basically try to finish up here. So there's a topic model, which is the kind of thing people here do at Google. You can solve some interesting problems with that. In particular, let me show maybe one picture that'll give you a flavor of this. Yes, you can have Chinese restaurants now arranged in a tree. You can have a Chinese restaurant at this thing and one at this thing. And you can have infinite, this is the first night you go to a restaurant, and you pick a table, and that tells you where to go to the next night, either here, here, or here. And the next night you go to this thing, there's another infinite set of tables. You pick one there, and you go down a certain branch. So this is now a random branching tree. And you get a probability measure on it. It's infinite, but that's perfectly fine. All right, and now you can do cool things like you can take in, all right, here's maybe a more interesting one to you. You can do these topic models on infinitely branching trees. You can build at every node of one of those trees a list of the most probable words that have, of documents that are following paths in this tree. So at the very top, it turned out that when we did this on the JACM abstracts over the last 10 years, that the words which occurred most frequently in all articles were the, of, and so on. All right, and those became the topic at the highest level of this branching tree. And then the next level down, the most useful words were things like algorithm, time, and the little letter n, which is what algorithmists used often in their papers. Queries, class complexity, programs, language rules, networks, network routing, and so on. So this looks like the curriculum of a computer science department. And then you go to the next level, and it becomes a little more precise and more precise. All right, so this is what this was a nice example of probability theory in action. We didn't have any tunable parameters here. We gave it the data of the JACM, and it has now a random probability measure under it. It infers all of that structure, all those words, all the probabilities associated with that. All right, so that's a nice example, I think, of this kind of thing in action. And then the last slide is just as a statistician, you worry about, will this really work? Can I prove, given some data, that this thing will, as I get an infinite amount of data, that this will prove and converge to the right answer? And the answer is no, you cannot. There is counterexamples to that. You cannot prove that in complete generality. You do not have consistency in the nonparametric world. And here's an example where you lose it. But there are now some positive results for certain kinds of neighborhoods. You can't get it for weak neighborhoods. You can get it for Hellinger and Kullback-Leibler neighborhoods. And this is actually an ongoing problem in statistics, is to try to characterize things like consistency and weak convergence for these random measures. OK, so sorry to give kind of a highly technical talk at the end of the day. But I hope you found it interesting to see this area. It's based, as a statistician, I find this an exciting area. I tend to be a Bayesian statistician, and most Bayesian literature has been very parametric. You make a lot of really strong assumptions, and then you show that it works. But this is a way of sort of not having to make those kind of strong assumptions and be non-parametric. And then I hope to try to convey a little bit of the reason this is exciting mathematically. There's a lot of combinatorics and graph theory and probability all being mixed together with infinite objects here. And there are quite a number of open problems, some of which I've alluded to, and there's many others. Okay, so I gave a tutorial on this past year, and there's a long bibliography with literature references and so on and so forth. So if you're interested, please have a look, and you'll see the tutorial. Okay, thanks.
I see tired faces. Well, if you have questions, you can ask the speaker at dinner. Or,
He's not coming to
okay.
Yeah,
Or
sorry.
Anyway, dinner is at 6:30. The directions are up there, so at some point we will all migrate over. Let's thank all the speakers for today.